So hello and welcome to another video in this quick revision series. And in this and upcoming one or two videos, we'll revise chapter 5, current mirrors. And as we have already stated right at the start of this playlist also, that we won't like discuss each and everything. This is just a really quick revision so that I'm able to know that all my concepts are in order. And if anyone wants to just get like a really quick gist of things, they are free to see. And if they find anything wrong or faulty with my approach or thought process, then you can always correct me, right? Okay, that out of the way, let us discuss this chapter. And with while starting this, I want to just pose one question. We already know what is the need of current mirroring because we know that to bias our circuits, we need certain amount of bias current. Now, to have that bias current, we also need some bias voltage. And in on chip, it is typically not straightforward to generate bias voltages, and so the circuit designers have found this as to be one of the best approach is to have a single bias current, which is typically they call it as a golden reference, which is supposed to not change with process variations, and then they try to mirror it in different parts of the circuit, depending upon how much portion, fraction, or multiple of that reference current is needed in the circuit. And using that bias current only, we can also generate our bias voltages. And that's the basic idea behind current mirroring, that you are taking current in one section of the circuit and you are making its replica in another section of the circuit, or maybe a multiple of it. Great. So that being straight to clear to us, now let's just look at this basic current mirror. And is now my question is that will this guy function as a current mirror? So that's the fundamental question over here. Will this guy function as a current mirror? So the point here is that let us assume that the M1 and M2 have same sizes. So will IRF current appear at I out? Will I out be equals to IRF? Because the basic configuration of current mirror which we have seen is that I have this transistor M1, but it has its gate and drain shorted, and then you connect it to this guy, and then you have your output. And now you say that I out is equals to IRF if their aspect ratios or W by L ratio is same. So uh, if we know already from our textbooks that this guy works as a current mirror, but will this guy also work as a current mirror? And the argument again, which we can make here, is that the gate source voltage in both of these guys is equal. So shouldn't the current be equal? So no, this guy won't work as a current mirror. Why is that so? Is because here in this tip circuit, we have ensured the condition of saturation. What this means is that since the gate and drain are shorted, this transistor is always in saturation, which means now that the current IR which flows to this transistor is purely a function of overdrive voltage, right? Whereas in this case, there is no constant on this transistor to be in saturation because its gate and drain are basically loose or they're not tied together. So this guy can be in triode saturation, it can be in any regime of operation, and it can still allow flowing IRF current through it. This implies that since the node voltage at this terminal, which I'll call V out, is also not known to us, so that means that you can't ensure reliable mirroring of current from here to here. That's the basic idea here. And here, on the other hand, we have already ensured that this transistor is in saturation. And now we'd say that now this guy also will mirror current only when its V out satisfies a certain minimum voltage. That is also worthy to mention, but we should appreciate the fact that when this reference transistor is not ensured to be in saturation, then definitely it won't work as a current mirror. This guy also will mirror current effectively from IRF to IR out only when this transistor M2 is in saturation, which means that there is a certain constraint on the swing limit of this V out node. and this brings the problem also of the swing limitations. Although this is a very simple circuit, very basic current mirror. So if I'm saying that there is for IRF there is a voltage drop of VGS, so we now know that the minimum voltage which should be present at V out is equals to what? It is VGS minus VT, which is basically quite a very small value. So we can say that yes, the swing of V out, the lower swing limit of V out is quite low, so which is a good sign, right? So we can here, if I'm mentioning my advantages, I can just say that the V out min for mirroring to happen is simply equals to 1V overdrive, right? Because VGS minus VT is 1V overdrive. Again, I am assuming that since the technology is symmetric, so the threshold voltage and all is symmetric, but as we already know, nothing is perfect, as we were discussing in the last differential amplifier series also. So yes, because of VT mismatch and all, current mirroring might not be that accurate, but for now, we are assuming threshold voltage same everywhere. Now, the disadvantage over here, we can understand it better when we consider a very important effect, which is channel width modulation. And we know that typically when you derive I out by I in, so you know that you can just write it as what you can write it as is that since both of the transistors are assumed to be in saturation and assuming that V out min value constraint is satisfied, so when you divide the two currents, you will find yourself left with only the aspect ratios, right? So that is like VL2, VL1, but because of channel length modulation, an extra term appears which is lambda VDS2 and 1 plus lambda VDS1. And so because of this guy, the current mirroring is not that accurate, right? And again, because this VDS2 voltage can change since it is at this output node, which is basically floating, and basically this node voltage can basically change depending on circuit which is connected here. So that's one issue with the circuit, which is basically of accuracy, right? That you won't be able to accurately mirror current from here to there. Great. So that out of the way, now let us discuss some other basics. That is, for example, I have so this IRF current. So how would I ensure that in this branch or maybe this analog circuit has two IRF current? So one way is clearly that I am having only one transistor in the segment and I'm keeping its aspect ratio double of this reference transistor. But let us say that I don't want to play with my aspect ratios. So what I can do is that just I can have two transistors parallel. Both of them will have plus VGS and plus VGS, which is same as the drop across this reference transistor. And if you keep them in parallel, you will have two IF current. Similar philosophy is used here, where you can see that plus minus VGS appears here, and also since this node goes over here, and basically we are not able to see it straightforward, but basically these two transistors seem to be in series, and effective aspect ratio seems to be W by L half if this aspect ratio is W by L. Similarly, effectively, this whole thing seems to have its aspect ratio 2W by L. If we have time, this is quite obvious, but if we have time, we'll try to prove this guy, okay? That this is actually happening, assuming again that all these transistors mutually have same W by L, right? Okay, going forward, another alternative was that in your reference transistor only, instead of having one reference transistor, you could have had two reference transistors in parallel, and so that each of them carries IR by 2 current, and now you can obtain the currents in fraction, right? So that is another way, and I think it's not that big to understand. Another thing that we must realize here is that typically sizing or current mirroring is done only by changing the W of the transistors. That is the weight of the transistors. And why is that so? It is so because if you try to mirror currents by ratioing lengths, it does not typically work for two reasons. Okay, why is that so? One is L effective. L effective is typically equals to L minus 2L dash, where L dash is the depletion region which penetrates from source and drain ends into the channel, which basically depends upon again your VDS. Yeah, right. So since length is varying with your basically bias point, basically because typically because of the gauge drain to source potential, you would not want to mirror your currents by taking ratio of length. Another thing to keep in mind here is that even threshold voltage is a function is a function of length, as we know, right? Even threshold function is a function of length. And to be more precise, what happens is that it basically uh, decreases with the length, right? For at a certain point of time, if this is the graph voltage and this is like graph of L. So these are the two reasons that we'll not use width to basically mirror our current, and we'll only use width to mirror our current. Going to the next, now we already discussed the disadvantage of the basic current mirror. So the idea now is to that we would want, if I want to mirror current through this guy, I'll typically want that this Vx, the node voltage of this Vx is not changing much, right? So the basic idea is that I would want it to be perhaps shielded. Like if I see, if for basic current mirror, which I drew above, if I try to sketch the characteristic, okay, for example, I'm drawing this current mirror yet again, and this is M1. I'm connect diode connecting it, and then here I'm having my current mirrored, I out, and for time being, let us just assume they have same aspect ratio, and here I have my node voltage, let us call it Vx, okay? So if I try to sketch I out with respect to Vx. So we know that for a certain Vx, this guy won't be in saturation, right? So we know at what after what voltage will this guy go into saturation when Vx is equals to 1 V volt drive, right? And here now current will be mirrored, but because of channel length modulation, which is basically you can describe it by 1 plus lambda times Vx, current will instead of being equal to Iref, considering both have the same W/L ratios, current will kind of uh, go like this with a certain slope, right? Which may basically is kind of similar to the output characteristic of transistor, and this finite slope, which is because of channel length modulation. The idea here is that if we want IRF to be exactly same to our I out, then we would want this slope to decrease, or alternatively we would want that our output resistance or the basically increases, right? That output resistance for I out increases. That's the basic idea. And yes, if I were to sketch the complete graph, then yes, again this guy will fall off, right? It's basically just the output characteristic of the transistor if you really think about it. Great. So that out of the way. So now we can appreciate the fact that we basically want to shield our node voltage Vx, and also we want to increase the output resistance. The best way to do that is to put a current controlled current source because it has infinite resistance at the base. Most simple example that you can think of it is a common gate stage. And after placing the common gate stage, the circuit kind of looks like this. And alternatively, you could have said that to increase output resistance, you convert it into a cascode, which is basically the same thing. And we already know that cascode has resistance of the order of R naught square times Gm, and which is pretty huge, considering the fact that initially our output resistance was only R naught. So that being said, now the challenge here is that you should generate the V bias voltage such that you are ensuring that both of these transistors are in saturation. Okay. That out of the way, now let us try to discuss about how this current mirror is functioning, and how basically you are allowing Vx not to vary with process, and to allow Vx not to vary, the thought process we had was to basically shield it using cascode, or alternatively we wanted to increase the output resistance. Great. So now we know that if this drop is VGS, so Vx min will be equals to what? It will be equals to VGS minus VT, which is the simple boundary condition of a transistor at triode and saturation region. Then what we had was that since I'm taking all of these transistors to be identical in nature, identical in the sense that their thresholds and mobility and all are same. So you can understand that since this guy also carries I out, this guy also carries I out, and have the same W by L, so their VGS drops also will be the same. So basically V what is VB? What's the voltage at VB? That should be Vx plus VGS3, which I'm saying to be equal to VGS2, which is equals to VGS1. So the equation just becomes VB is equals to 2 VGS minus VT. And now, what will be the minimum V out to sustain this entire guy in saturation is again just that boundary condition, which is 2 VGS minus VT, correct? Uh, is this correct? Oh, wait, VGS minus VT. So yeah, there should be one more VT drop over here, and this is the expression we are looking for. 2 VGS minus 2 VT, right? And alternatively, I can write this guy as 2 V over J, correct? But again, the thing here is that we have chosen our VB as 2 VGS minus VT just so that our VX could be at minimum operating potential. And then we from that we conclude our VB value should be this. And from that we are getting our V out minus 2 V over I, which again is a 1 V over type increment over the basic current mirror, and we call it a high swing cascade because again 2V drive is also not a very big value, still a small value. And to be able to appreciate this more, should be able to understand that in smaller nodes like 180 nanometer nodes, typically our VO drive values are between 600 to 700 millivolt. Okay, so I'm saying this right away right now because we'll be able to understand this more. But that when you will have two V overdrive plus VTH, so you can understand that that VTH term basically can drastically change your swing limits, especially in low node technologies, right? In low node and low power technologies. So yeah, our out is increasing and our swing is also not that bad. Like our our output swing is still quite fine because the value of your min is low. But again, accuracy is compromised. And can you now guess why accuracy is compromised? If you see, our initial problem with the basic current mirror was again the mismatch of VDS1 and VDS2, the drain to source voltage. Here also we are saying that Vx is equal to VGS minus VT, and here this node voltage, which is equals to this gate voltage, is equals to VGS only. So again, since drain voltage is a mismatch, so the accuracy is compromised. Now another problem with the circuit again is to how to generate VB. So that's the issue that we have. So, but the main problem is all about accuracy. That we are not. It is a high swing cascade, but the accuracy is low. So if we are able to appreciate this, we can move further and go to alternative. So initially we designed VB or set the value of VB so that the value Vx could be minimum. Now we can appreciate this fact that the gate voltages, like if I just redraw that configuration, I'm not drawing the entire thing, but yeah. So okay, I have basically drawn the entire thing only, but yeah, that doesn't matter. So okay, so the thing here is that if you want this and this node voltage to be the same, that means that this guy value should also be equals to VGS. So what should be the value of this guy? The value of VB then should be twice of VGS. Okay, so we have to generate VGS such that the value at this potential, which is basically Vx, should be equals to VGS, and then you can ensure that the accuracy will be there. How will you generate twice the gate overdrive, twice the gate to source voltage? The one idea that comes to mind is that if you keep two transistors in saturation having the same W by L ratios, then yes, you can achieve twice the VGS value. And that's what we have done here in this circuit also. So here I have just written here to prevent the effect of VDS1 not equal to VDS2. You can just generate your VB such that VB minus VGS3 is equals to VGS1, and you can have assuming that VGS3 equals to VGS1 and so forth, so on and so forth. You can just say that VB is equal to twice of VG as VSG. I should write this as VGS since we are basically dealing with MOS transistors. So it is basically VGS. So VB is equals to twice of VGS, and it can be given by two transistor series, and V out min now is be equal to 2 VGS minus VT. So here you can see that here there is one VGS drop, and then again another VGS drop. So this guy is 2 VGS, and here you have 2 VGS. So this is VGS. So we have basically achieved accuracy, but we are losing out on what? What we are losing out on. And another disadvantage, which I'm not basically stating, it's quite obvious that we need more and more transistors, but that's not a big deal. So this disadvantage here is It is a big deal actually, yes, that you are losing out on area, but that is inevitable that we already know that. And the main problem over here is what? That since you are generating twice the VGS. So the drop here required is 2 VGS minus VT, and if you want to write it in something familiar, it is basically 2V over drive plus VT. So as I discussed before, the 2V over drive is not a problem, but VT is quite a huge voltage in low node, which means that the swing of this guy is limited. So it's not a high swing cascode anymore. So it has accuracy. So this configuration which we have drawn, it is high accuracy but not high accuracy. Yeah, it's high accuracy, but the swing is not high. The swing is poor, right? So that's the basic idea. And now again, the thing here is then how can you generate VB? So one of the methods we already saw how you can generate VB. This Razavi has another examples where you're basically using a resistor to generate VB. And that is yeah, that is something that you can utilize. And then the more advanced versions can be that now you're using this resistor in a transistor, right? And you're biasing transistor in triode regime to act as a resistor, and then you can have all these various methods to basically generate your bias voltage. Moving on, again, I would want to basically summarize and actually want to emphasize over is that in low swing cascode or poor swing cascode rather, okay? So I'll just write it as poor swing cascode. What we were seeing is that accuracy was there, but the swing was limited, or V out min was basically limited by V overdrive or twice of V overdrive plus VTH. And in low accuracy cascode, which was also high swing, we were having V out min limited only by twice of V overdrive, right? So the main idea now here is that in this guy, there are various ways to basically generate VB, and in our quest to ensure that this node voltage, basically Vy, is equals to Vx. And we'll come back to it. And now, what remains to be discussed further down in this chapter is biasing techniques and active current mirror or differential pair with active load or the five-stage OTA. So, we will discuss that in the next video. And thanks for watching.